So I want to start by thanking the organizers for giving me this opportunity to speak here. I'm going to talk about morphological statistics, and it connects very nicely to the previous talk, where this can be used as one of the ways to do parameter estimation in cosmology. But I'm a little shaken because if the FBI really works fully, then we'll have to throw all this out. Okay, so before I start, I want to mention that this is the work that I'm going to talk about is a team effort. A lot of people have contributed important contributions to the work. So here are some of the people. I have not shown all the photos. I've only shown photos of people whose work I will talk about. In particular, I want to draw attention to Suveda, who is in the audience, and she'll be having a talk tomorrow, and Kanan, who is my recent PhD student. Okay, so so when we study cosmology, the fluctuations, the observational data that we have, which are fluctuating in space, we are modeling them as random fields. And as random fields, how do we extract physical information from the data? That is by calculating various statistics that we can compute from the field. So here is an example of the field. So we've been hearing about the global signal, in particular for the case of the 21 centimeter, for example, global signal is there. And then one way is to do mode decomposition, and we calculate power spectrum by spectrum and so on. This gives us physical information of the field, all the physics that is going in the field. An alternative way is to look at morphological statistics, which means that we construct excursion sets from the field or field levels, and we construct binary maps from field levels, and we look at the geometry and topology of those excursion sets. So instead of having the modes as your variable over which you are going to deconstruct your field, in this case, we have the field levels. So the threshold that we choose that acts as the as a way to look at separate out the information. So I'm sure most people are familiar with many of the words here: Minkowski functionals, Betti numbers, tensorial Minkowski functionals, counts of critical points. There may be more. So I will focus on these three. And so here is the plan of my talk. I will talk about theoretical developments that we have made in the recent past in understanding this morphological statistics. So this is going to be in this, as Tirth said, this is an era of machine learning. And in this era, I am going to appeal to you to take a step back, and we are going to look for things that we can push in deriving analytic expressions for various of these properties. So these morphological statistics, I am going to, at this stage, I will probably not care so much about applications, but I want to understand theoretically what are the ensemble expectations of these statistics. There is a lot of progress previously made, and what are the things that we have done to push forward the understanding. So I will particularly talk about ensemble expectations, the effect of, if in the presence of a contaminating field on the true signal, can we calculate analytically the bias that the contaminating field has on the morphological properties of the true field? And thirdly, I will mention briefly about how do we go beyond ensemble expectations? Is it possible to predict, for example, uncertainties? So this has not really been discussed in the literature previously, and this is what I'm going to present a little bit of progress in these directions. And finally, I will apply to understand gravitational evolution of large-scale structure, just one slide, and some understanding of using morphological statistics and the EOR to discriminate cosmological models. Okay, so let me start by giving a definition of the morphological statistics. So in 2 dimension and 3 dimensions, here are the excursion sets. So these are the levels. You choose a level, and above that level, you have the special regions where the field is defined. And that's why you have, so if you go from a very low threshold to a high threshold, or high threshold to a low threshold, you will have structures, the spatial regions being broken up into these fragmented pieces like this. So clearly you can see that there is a lot of interesting geometry and topology, and how to capture that is, they are captured by something called in a unified way by something called the Minkowski tensors. So these are quantities which have the tensorial components here in the index. So in the 2D, there are 3 of them. So for every, you have these boundaries of between the black and white regions, and similarly, you have the boundary between surface areas which are enclosing the connected regions. So basically, these are looking at these quantities. There are 2 basic variables. We are looking at the position vector and the normal vector to the boundaries. From this, we can construct this set of tensorial quantities, rank 0, 1, 2, and so on. And in 2D, the important physical quantity is the geodesic curvature of the boundaries, which tells you how they are curving, how they deviate from straight line. And in 2D, we have 2 curvature quantities, G2, which is a mean curvature. When you have a surface, you have like the geodesic curvature along lines, and the mean curvature is the average between the maximum and the minimum. And we have the intrinsic Gaussian curvature of the surface. So this is how we define. And from these, the rank 0 ones are the Minkowski functionals. They quantify the area, perimeter, and count. So V0, V1, these are the geometrical quantities. V2 is a topological quantity. And similarly, in 3D, we have this. So the tensorial ones, rank 2 ones, they provide information about how the excursion set, the connected regions and so on, they are elongated or aligned. That gives us that information. And in addition, we have Betti numbers, which are counting the holes and the connected regions here. So BC and BH are the holes and connected regions. In 3 dimensions, we have one more, which are there can be tunnels which develop in excursion sets, and that also goes in. And the last Minkowski functional is related to the Betti numbers in this way in 3D and this way in 2D. Okay, so having introduced the morphological statistics that I am interested in, so I'll just give you a little bit of history about the ensemble expectations. So the interesting thing, at least from a theoretical point of view, is that we can relate, given the nature of a random field, we can relate that to how the morphological statistics vary as a function of threshold. And in particular, for Gaussian field, of course, it is one can compute analytic expression, closed form analytic expressions that is given by this first expression here, Hermite polynomials. K is the different Minkowski functionals. And so for cosmology, we are interested in mildly non-Gaussian. Okay, there are lots of non-Gaussian fields, but what we can compute by analytically is by pushing from, if you go from Gaussian to mildly non-Gaussian, can you compute the formula? So this was carried out by Matsubara in several, also Dmitry Pogosyan and his team, they have calculations of non-Gaussian deviations. So the point here, the expression looks complicated, but the point I want to highlight are the skewness parameters. When you are looking at the Gaussian formula, you have Hermite polynomial and a coefficient here. The cosmology dependence is here, AK. And AK is basically dependent on an intrinsic scale in your field that you introduce, which is sigma 0 by sigma 1. So sigma 0 is the variance of the standard deviation of the field. Sigma 1 is the standard deviation of the first derivative of the field. And that basically controls the amplitude. So the connection of this with the power spectrum and bispectrum comes via this. So you can clearly see that it is an integrated, all the mode information that one has in the power spectrum is integrated, and it is condensed in the amplitude here. And that is why it has less constraining power if you are going to look at how physics affects different modes. So that's one thing. Then when you go to non-Gaussian, mildly non-Gaussian deviations, you have the skewness. There are 3 skewness parameters. The S0 is the usual one, and the other 2 are involving the field derivatives, first and second derivatives. These are the rotationally invariant 3-point functions that you can, 3-point correlation that you can construct. Similarly, in the next leading order, you can have these kurtosis components involving the derivatives. Okay, so this is known previously, and so we have the Gaussian formula are like this, and what we are interested in is mild deviations from these shapes, Gaussian shapes. Okay, so that was for Minkowski functionals. So we can ask about what about ensemble expectations for the tensorial second rank tensors. So that is something we computed over the past several years. So we had computed for Minkowski tensors. So the point to note is that Minkowski tensors for isotropic random fields, they do not contain new information compared to the Minkowski functionals. And that is what we have shown in many papers. But it becomes very interesting when the field is anisotropic as well as non-Gaussian, and that is work in progress. So I don't have anything to report here. Then for Betti numbers, you can also ask what are the ensemble expectation formula, and that has not been known. This is a very hard problem that several people, particularly mathematicians, have been trying, and we don't know the full analytic form yet. However, in the recent past, what we did is we looked at an approach to calculate the analytic expression by involving the total absolute curvature, which is given by this formula here. It's an integral over kappa. So so what you can see is that if I don't have the magnitude here, the absolute value of the curvature, that quantity gives us the Euler characteristic, which was one of the Minkowski functionals. Okay? Because the plus minus, the curvatures, they will cancel out, and eventually this will add up to 2 pi. And so when you cancel, it gives a count of what is the number of the structure there. So we looked at the total absolute curvature, which is because we are throwing away, by canceling out the negative curvature parts, we are throwing away information. If you retain that, can we compute this? So we were able to compute the analytic expressions for this. I'm not showing that here. But what it led us to is that K will contain, it's a sum of the Betti numbers as against the Euler characteristic, which is the difference of the Betti numbers. And we could get a piece of the expressions for Betti numbers. So we are not there yet for the full expression for Betti numbers, but we could calculate a piece of it. Okay. Then the next question we addressed is, if I have a true signal and some contaminating field, which I'm denoting by V, is it possible to compute analytically how the morphology is biased? Morphology of the true field is biased. And we showed that it is indeed possible to do it for up to mildly non-Gaussian fields. So here is how the morphology is is an example of some V field which has been added to the signal, and it is changing the morphology. But we can do this in a controlled analytic way. We can determine what is the bias. And that for the strategy for that is to write down the Minkowski functionals for U, for the signal field, and then determine what is the bias. And for this, we introduced 4 spectral ratios: the signal to noise, inverse of the signal to noise, then the inverse, the ratio containing the first derivative of the fields, and the cross correlations between the two fields. So doing this, we could, for example, I will demonstrate two examples, some of a Gaussian signal and some Gaussian noise with some power spectrum. And so this is how the amplitude of the Minkowski functional gets biased. This red color is the factor. And to our surprise, we found that it can increase the amplitude. So usually when we think of noise, at least in my mind, I had that noise will increase the amplitude. But we found that by the full general expression, we found that it can also drop depending on what these spectral parameters are. So this is the demonstration of the analytic formula and the numerical result. So we did this with CMB. Then the next example is if you have a non-Gaussian CMB map with an FNL type non-Gaussianity and you introduce noise, how will its morphology change? So for this, we started out by computing first just the PDF. How far can we go by determining the PDF? So this is my student, Vidya Ganeshan, in her paper, we had shown that for FNL type non-Gaussianity, this is the form of the PDF of the field. And to that, we add this noise, and then we can derive the PDF of the composite field like this. And you can see that the FNL parameter gets modified by the function of the spectra. So this is the bias on the FNL parameter. And as you increase the signal to noise, maybe for around signal to noise 4, we are getting like 10% accuracy. So this expression will affect the skewness parameter, this one. It directly gives a prediction for this. However, for the other skewness parameters, which involve the field derivatives, we don't have that expression. But by plugging it into the Minkowski functional, we can determine what the bias factors are. So now, this is a demonstration of how the analytic formula and our numerical computations match. So this gives a good analytic handle on what the contaminant field is doing. So the potential application of this is in, for example, understanding residual foregrounds in CMB. I would not go so far as to say in EOR, because in EOR it seems that the level of foreground is too high, and so this will not work. Okay, then the third point I want to stress is about predicting, going beyond ensemble expectations. And we had a lot of discussion in the previous talk about likelihoods and so on. We usually assume, if we were to use these statistics for physical inference, we will assume a likelihood, and what do we choose? I mean, is it correct to take them to be Gaussian or not? That is the question we address. And particularly, it's a very hard problem. It's very difficult. So what I did is I thought, okay, let me look at only the topological quantities, because usually topological quantities are easier to manage. So for that purpose, what I did was we look at the two Betti numbers. This is in 2D. I will not talk about the 3D because in the interest of time. So we have the Betti numbers and the Euler characteristic. So what I did is to introduce these numbers as sums of random variables. So let us see how I do it. So this is a typical excursion set. The yellow regions are the connected components, and we can have holes in them, which are the black regions, not the big black regions, but within the connected region. So clearly, when you look at this, you can see that this excursion set consists of structures of this type, which have no holes, simply connected regions, structures of this type, which have one hole, and so on. So the number of holes can increase, and so this is like a topological basis set that is being introduced here. And when I say Betti number for this excursion set, it will be a count of how many of each of these is present. Okay. So I am introducing these variables mj. J is going to go from 0 to what is the largest structure possible. That's the possible. And we can write down the expressions for the Betti numbers and the Euler characteristic in this form. So I have transferred my ignorance of the statistics of these variables into now these counts, M0, M1, M2, etc. What can we do with that? So what we can do is that that helps us. So basically the first point is that each topological quantity, I'm expressing it as a sum of many different random variables. And so clearly you can see that the emergence of possibility of using the central limit theorem, if these MJs are independent of each other, or at least block independent of each other, and the J max is very large, in that limit you can hope that they will tend to be Gaussian variables. So that's a hope. But then we can see that, so let's look at this part first. We can see that the Betti numbers, in the limit of high positive threshold, you would have all seen that the structures, the external set will consist of isolated structures, and the number will grow up to maybe around nu equal to 1 sigma of the field, and then it will drop. So in that regime, Betti numbers go to M0 only, okay? And holes go to 0. And similarly, in the negative regions, the BC goes to 0 and BH goes to count. So this is it just tends to become the sum. It is no longer a sum of many random variables. It's just one variable. But okay, we need the information about what the statistics of these variables are. If they are like, if M0 is like a binomial distribution, for example, for a large number with a large mean value, then there is hope that it will be it will have Gaussian distribution. So the summary from this exercise is that the nature of these three topological quantities strongly depends on the threshold and also basically the power spectrum. I did not have time to stress that. And that at large thresholds of around 1 and higher, they are clearly not Gaussian random variables. So it's not a good idea to use them for inference as Gaussian random variables. So here is a plot. Actually, I'm exploring the computations of the M0s, and this is Dmitry Pogosyan very kindly extended his code to do one sample calculation, and here is how the MJs distribute as a function of threshold and at the different J levels. Okay, so that is the end, so I don't have much time. Very quickly, I will go to some actual physical application. I think I'll skip this gravity part, and I will talk about how this morphological statistics can be used to add additional information to other statistics, power spectrum, and the global signal, how they can discriminate models by adding more information to these traditional statistics. So here is in particular, to demonstrate this point, I use one model. There is a model of inflation called which has particle production happening during inflation. And because of that particle production, it enhances the primordial power spectrum at specific scales, which depends on the model parameters. It introduces a bump of this type. So this can be modeled with two parameters, the location of the peak and the height of the bump. So these are the two parameters. And this is the model that Suveda has studied, and she will discuss it in more detail tomorrow. And so what we did, so in short gist of what Suveda will talk about is that we compared this, we simulated using 21 centimeter fast different models with, for today's discussion, let us fix the EOR parameters, and we have different fiducial model. The fiducial model has the power law form, and the feature model has these different parameter values. And what Trivida had found is the existence, I'm almost done, last slide. So she had found the existence of a particular scale of K peak at which the global signal cannot distinguish at all. And she will talk about the power spectrum, which can distinguish it further. But what I want to mention here is about the topology using the Minkowski functionals and Betti numbers and so on. We computed those. And this slide is to show how this morphology can distinguish the different models. So in particular, KP, which is the green color, you can see that these are the deviation plots between the model and the fiducial model. So we see clear distinctions of this, which was not possible to be distinguished in the global signal. Okay, so that brings me to my summary. Yeah, maybe you can read. Thank you for your attention.
We have time for a quick question.
I mean, this is a totally naive question, but you mentioned that it was really difficult to get these analytic expressions for the Betti numbers.
Yes.
Is there a sort of a simple way of understanding why it's so hard?
So, I can use this slide. So what happens is when we calculate Minkowski functionals, for example, so Minkowski, the third Minkowski, in 2D, the third Minkowski functional is the Euler characteristic. And that the Euler characteristic is basically counting, you are integrating. So I choose okay, maybe I use another. Sorry, I'll use the excurrent set. Okay, this is better. Okay, so here, when we do the analytic calculations, what goes in is the joint probability distribution of the field and its derivatives. And when you do that, you are integrating, you transfer the knowledge of the field. What we actually have in the formula is integral over curves, but then we translate it into a field over the entire range of the field by introducing a delta function with a suitable Jacobian. Okay? And in that process, that takes care of all the, so if you know, the connected regions are those which have the boundaries which are oriented in one way, and the connected, holes are the ones which have another direction. And it is very difficult to distinguish between these two and separate out the integral into these two parts. And that is the origin of the difficulty. And in our method, what we did is to look at an alternative way by, the alternative way is to say that, okay, I'm going to take the modulus of the total, the modulus of the curvature, and I will integrate, maybe I can calculate it. And this contains information of the sum of the two Betti numbers, and I can use that information to separate out the two. But it's a non-local quantity, so probably some, anomaly, what is it called? When you transport a vector along a curve, so those issues, the non-local issues come in, and those will have to be incorporated. That's why we could get only one piece. There's a piece still missing.
All right, if there are no further questions, let's thank Prava again and all the other speakers of the session.